Dijkstra's algorithm in calculating the shortest distance. Navigating the complexities of urban planning and logistics requires efficient methods for determining the shortest routes between locations. One of the most fundamental and widely used algorithms for this purpose is Dijkstra's algorithm. This study will delve into the inner workings of Dijkstra's algorithm. We'll explore its logic, provide a step-by-step breakdown, and illustrate its application with practical examples. What is Dijkstra's algorithm? Dijkstra's algorithm, named after computer scientist Edgar W. Dijkstra, is a graph search algorithm that solves the single-source shortest path problem for a graph with non-negative edge weights, producing a shortest path tree. In simpler terms, given a starting city and a map with distances between cities, the algorithm finds the shortest path from the starting city to every other city on the map. It's a cornerstone of network routing protocols and GPS navigation systems. The logic behind the algorithm. At its core, Dijkstra's algorithm employs a greedy approach. It iteratively explores the graph, always choosing the next node that is closest to the starting node based on the current information. This greedy selection ensures that the algorithm gradually builds the shortest paths from the source to all other nodes. The algorithm maintains two sets of nodes. Visited nodes, nodes for which the shortest distance from the source has already been determined. Unvisited nodes, nodes for which the shortest distance from the source is still unknown. The algorithm also maintains a distance table, which stores the current shortest distance from the source to each node. Initially, the distance to the source node is set to 0, and the distance to all other nodes is set to infinity. Step-by-step breakdown. Let's break down the process of how does Dijkstra's algorithm calculate the shortest distance to each city into a series of clear steps. Initialization. Assign a distance value to each node, set it to 0 for the source node and infinity for all other nodes. Mark all nodes as unvisited. Set the source node as the current node. Iteration. For the current node, consider all of its unvisited neighbors and calculate their tentative distances through the current node. For example, if the current node has a distance of 5, and the edge connecting it to a neighbor has a length of 2, then the tentative distance to be is 5 plus 2 equals 7. Compare the newly calculated tentative distance to the current assigned value. If the tentative distance is less than the current assigned value, update the assigned value with the tentative distance. After considering all unvisited neighbors of the current node, mark the current node as visited. A visited node will never be checked again. Select the unvisited node with the smallest distance value. Set this as the new current node, and go back to step 2. Termination. Repeat step 2 until all nodes are visited, or the smallest distance among the unvisited nodes is infinity. A case example, finding the shortest route between cities. Imagine a road network with 5 cities, A, B, C, D, and E. We want to find the shortest distance from city A to all other cities using Dijkstra's algorithm. Let's assume the following distances between cities. A to B, 4. A to C, 2. B to C, 1. B to D, 5. C to D, 8. C to E, 10. D to E, 2. Following Dijkstra's algorithm. Initialization. Distances, A equals 0, B equals, C equals, D equals, E equals. Unvisited. Iteration. Current node, A. Neighbors, B, C. Update distances, B equals 4, C equals 2. Visited. Unvisited. Current node, C. Neighbors, B, D, E. Update distances, B equals 3, D equals 10, E equals 12. Visited. Unvisited. Current node, B. Neighbors, D. Update distances, D equals 8. Visited. Unvisited. Current node, D. Neighbors, E. Update distances, E equals 10. Visited. Unvisited. Current node, E. No unvisited neighbors. Visited. Unvisited. Termination. All nodes visited. The shortest distances from city are A to E, 0. A to B, 3. A to C, 2. A to D, 8. A to E, 10. Applications of Dijkstra's algorithm. Dijkstra's algorithm finds widespread use in various real-world applications, including GPS navigation systems, finding the shortest route between 2 points on a map; network routing protocols, determining the optimal path for data packets to travel across a network; urban planning, optimizing traffic flow and designing efficient transportation networks; robotics, path planning for robots navigating complex environments; airline ticketing, finding the shortest flight routes with multiple layovers. Limitations of Dijkstra's algorithm. While powerful, Dijkstra's algorithm has limitations. Negative edge weights. It doesn't work correctly with graphs containing negative edge weights. In such cases, the Bellman-Ford algorithm is a more suitable alternative. Computational complexity. The time complexity can be significant for very large graphs, although various optimizations can improve performance. In conclusion, understanding how Dijkstra's algorithm calculates the shortest distance is crucial for anyone working with network optimization, route planning, or graph theory. Its simplicity and effectiveness have made it a fundamental algorithm in computer science and a cornerstone of many technologies we use daily. By grasping the underlying logic and applying it to practical examples, one can appreciate the power and versatility of this essential algorithm. References: Moy, J. OSP version 2. RFC 2328. Bellman, R. On a Routing Problem. Quarterly of Applied Mathematics, 16, 87-90.